Hello and welcome. These are the solutions to quiz 31. All right, number 1. Give the subshell for 3 electrons with the following quantum numbers. So electron 1 is a 3d. So the symbol d is given by the L value. P is given by a 1. F is given by the 3. And S, of course, would be L equals 0. All of these are possible quantum numbers. That's really not part of the question, but the range of m sub L depends on the L value for the electron. So the range of m sub L goes from minus L to plus L, all integers between, including 0. And then m sub S is either plus a half or minus a half. So we have a 3D, so 3 is just the n value, 3D, 2p, and 4f. 3b, 3p, 3d. So can't be A or C, then 2p, so the answer is D. Which of the following elements has the most valence electrons? Okay, so I just had to pull up a periodic table. So germanium's in the group of carbon. Carbon has 4 electrons, so does germanium. Chlorine's in the halogen group, 7 valence electrons. Chromium has a configuration, well, you expect the configuration to be 4s2, 3d4. The actual configuration being slightly different of a 4s1, 3d5 doesn't change the valence count. It's still going to be equal to 6. So we count any electrons in an unfilled lower subshell. We're always counting the outermost shell in the valence. It's just a question, do we also include some lower subshell electrons? If we look at chlorine real quick, as an example, chlorine has a neon configuration followed by a 3s2, 3p5. That 3 is the outermost shell, so n equals 3 is the outermost shell, so that's why we always would count the 5 plus 2 electrons for that particular element. Cerium is one of the lanthanides, element 58, but it only has 4 valence electrons. It only has 4 electrons on top of that xenon configuration. And then lead is also in the group of carbon, also therefore has 4 valence electrons. If you look at the configuration of lead, it has like a completed F block and a completed D block, so we're not counting those 14 or 10 electrons respectively towards lead's valence count, just its outermost shell. So it has a 6s2, 6p2 outer valence, so just 4 for lead. So that makes chlorine the correct answer because it has the most. Which sets of quantum numbers for 5 electrons of a multi-electron atom? Well, it says the sets of quantum numbers for 5 electrons in a multi-electron atom are given below. Which electron occupies the highest energy subshell? Okay, so let's just work out the subshell here. So we have a 4s, we have a 4p. I'm just looking at the n and the l values. We have a 3d, we have a 4s, and then we have a 3d again. Okay, and so if we're filling electrons in, if we're thinking of, okay, we're putting electrons in, maybe following along with the periodic table, like calcium, potassium, calcium filling into a 4s, then we fill the 3d next, and then we start filling into the 4p subshell. So the 4p subshell is the highest in energy. So you can look at elements in the periodic table and see that elements that are larger are last putting their electrons into that 4p subshell, so it's going to be higher in energy. Give the angular momentum quantum number for an electron in a 4p orbital. So the angular momentum quantum number is just the L value. So that's what we're kind of remembering here, is that this is just the L value. That's just given by the p. So for a p orbital, the L value is equal to 1. The m sub L is called the magnetic quantum number. And it, of course, has the range of minus L to plus L. M sub S is the magnetic spin quantum number, just to remind ourselves of the names of the quantum numbers. Number 5, what is the maximum number of electrons that may occupy the 4d subshell? So the 4d subshell, L is equal to 2, so the M sub L range is minus 2, minus 1, 0, plus 1, plus 2. That's where we get that there would be 5 4d orbitals. 2 electrons can go into each, so that's going to give us 10 maximum electrons in that particular subshell. So which electron has this particular configuration? So it's krypton followed by a 5s1, 4d, 5. We're just really counting the 36 electrons that krypton has. Use a periodic table. I'm looking at one right now. +1 plus 5 gives us a total of 42 electrons. And then we're just looking for an element that has 42 protons because this is simply an element, uncharged atom. So I'm looking for element 42, and that's molybdenum, or MO. Consider the ground state orbital diagrams of aluminum, silicon, phosphorus, sulfur, and chlorine. If you notice, that's simply across the 3p subshell, or the 3p block of elements. Which element has the most unpaired electrons? And so if we're imagining filling in from a 3s2, 2 electrons, into a 3p, we're going from a 3p 1, 2, 3, 4, and 5. So as we go from aluminum, would have 1 unpaired electron, silicon would have 2 unpaired electrons, phosphorus would have 3 unpaired electrons. Then sulfur back to 2, chlorine back to 1. So phosphorus is going to have the most unpaired electrons. Which transition in the H atom, according to the Bohr model, can lead to the emission of a photon with the greatest wavelength? So the greatest wavelength would be due to having the lowest energy transition. And then if we're going to have an emission of a photon, we have to be going from some high n value to some low n value. So we have to be going from some high n value, so say n equals 5 to like n equals 4, or just whatever, that this n value is bigger than this n value, so that we can get light given off. Because the H atom is losing energy, that energy is given to the creation of a photon. Okay, so the 1 to 6, 3 to 4 would involve the absorption of energy, or an absorption possibly of a photon. So we can rule those choices out. We're looking at 4 to 3 or 6 to 1. 6 to 1, of course, is going to be a bigger energy transition. So if we have 6 up here, 3, and then the gaps are getting bigger as we go down. This can't even draw it to scale on this particular page. Well, I mean, I can zoom out, but I don't feel like it. But so I think we can clearly see that the 6 to 1 is going to be the greater energy transition. So the delta E for this transition is going to be bigger. And that would cause it to have a smaller wavelength. We want the greater wavelength. So again, the lower energy transition is the one we're looking for. Lower energy transition is going to be the 4 to 3 transition. Okay, so a question like 8, be able to answer it just from the idea that our orbital energies from, say, n equals 1 up to 2, then up to 3, that these orbital energies are getting closer together as we excite. Eventually, we get to some n equals infinity value. And once we reach infinity, you can sort of see that the electron would become ionized and removed. And so the difference of energy here is actually just what we might call our ionization energy of H. So at some point, hydrogen can become ionized. If you imagine the alternate scenario, if you imagine a case where the orbitals are getting even higher in energy, if you say, okay, well, what if the atom did this instead? The orbitals are getting higher in energy as we excite, then you could never remove the electron and it would never become ionized. And we know H plus exists, and that would seem unlikely. So you can kind of remember this relative orbital energies, just if you think about the physics or the relative energies of the H atom. Moving on to number 9. Which diagram for oxygen is or are wrong because of a violation of the Pauli exclusion principle? The Pauli exclusion principle is the one that says each electron must have a unique set of 4 quantum numbers. There's also a rule of Hund's rule that says the electrons should be distributed into different orbitals and their spin should be maximized. So if we look at B, this is a Hund's rule violation. Because Hund's rule says that we should maximize the spin of the electron, so this one should have been drawn with a spin up. So this electron here should have been drawn spin up to be correct. So, but that's a Hund's rule violation, not a Pauli exclusion principle violation. This one here is a Pauli exclusion principle violation. Pauli exclusion principle says each electron has to have its own unique set of quantum numbers. These two electrons have the exact same magnetic spin quantum number since they're shown with the exact same spin. So C is the right answer here. Now A is also wrong due to a Hund's rule violation. So this is also a Hund's rule violation, which says we should spread the electrons out, use multiple orbitals, and maximize their spin. So this spin down electron here should have been drawn spin up over here. But that's a violation not of the Pauli exclusion principle, but of Hund's rule. All right, that's all for this video. Thanks for the attention.